In this video, we're going to solve a static equilibrium problem that involved an object on the verge of tipping. This problem comes from Giancoli's textbook, which is the source of many of your problem set problems, as well as an occasional test question. It presents you with a table, an unusual two-legged, two-dimensional table, but we're suspending disbelief here for the sake of physics. You're given the information about the table and you're asked how close to the edge of the table can a 66 kilogram person sit without tipping it over. So if a person's sitting right here, how close can they get to the edge? Now I've just changed this to cat because I always thought that if I was going to put videos on YouTube, they would be cute cat videos. So this one is. All right, so we've drawn the table. We need to show where all the forces are on the table. So let's start drawing forces. First of all, each of the legs is touching the floor. So there will be a normal force at each leg. You have to consider the mass of the table as well. This is totally symmetric. We take the whole weight of the table as acting right in the center of the table. And then we will also have weight from our 66 kilogram cat. Again, suspending disbelief. So we will label these forces normal force 1 for the first leg, normal force 2 for the second leg, force of gravity on the table, and force of gravity on the cat. Now I want to talk about tipping problems. Right. If the cat's here, nothing is going to tip, right? You'll have total symmetry and you'll have equal normal forces. But what's going to happen as the cat moves over towards the right side of the table, more of the cat's weight is going to be supported in this leg and less on that leg, and even more so as it goes further and further to the right. So, at some point, this normal force is going to get all the way down to 0. This is where you're in danger of tipping. Tipping is when this leg loses contact with the floor. So to solve for the exact moment of tipping, you need to solve for the normal force here becoming 0, but while the whole system is still in static equilibrium. So in any tipping problem that you see, that's what we've got. Your tipping condition is static equilibrium as your normal force becomes 0 where contact is lost. So we'll be solving this problem with that force equal to 0. All right. So as we've seen, your conditions for static equilibrium the forces have to add up to 0 and the torques have to add up to 0. Forces first. Your x component of forces add up to 0. Well, I think that's not going to be very helpful to us in this case. Normally it will be. Our y forces also have to add up to 0, and we do have y forces upwards. We've got the normal force in the second leg, downwards the two gravitational forces. Now we can figure out what those are. The table is 196.2 newtons. The cat, 647.5 newtons, taken from the masses of 20 and 66 kilograms. And from there you can solve for a normal force equal to 843.7 newtons. Great. All right, let's move on now to the torques. Our first job is to decide what the pivot point is. I think in this case, we will choose the point at which the table is actually pivoting. And remember, the first normal force is 0, so we'll just be dealing with the two torques from the gravity on the table and the cat. So, summation of torques is 0. So that's sum of R F sine theta equals 0. Now on the last video, I showed how in calculating torques, you can continue on the line of the force and then drop a perpendicular from your pivot point, and then instead of using the diagonal and the sine theta, you can use the length of that perpendicular times the force. And we're going to do that for these two forks because it's going to be easier. It's not always easier, this time it is. So for the torque from the table, the legs are 1.2 meter apart, so that's going to be 0.60 meters. That's a counterclockwise torque, so it's positive. So we'll take 0.60 meters times the force of gravity, 196.2 newtons. For the other torque, okay, now we don't know how far away this is. We're getting into the territory of what's our unknown. The question says how close to the edge of the table can the cat sit. So we want to solve for this. We'll call that distance d, which is not too helpful in calculating the torque. So I think we will first solve for this distance x, and then we'll just do a little arithmetic at the end to get d, because then the torque will be that distance x times the force, which on the cat is 647.5 newtons. All right. And then you go put that in your calculator and you'll find out that x is 0.18 meters. All right. So given that this whole distance from the table leg to the edge of the table is 0.5 meters, then this d that we want to know will be 0.5 meters minus 0.18 meters, which is 0.32 meters. And we can then say, therefore the cat can get to within 32 centimeters. of the edge without tipping. Okay, so to sum up, we followed our framework for static equilibrium problems where we set the forces equal to 0 and the torques equal to 0, then went to the x and y components of the forces. This situation had no x components. The y component allowed us to solve for the normal force in the leg, which you may have noticed we didn't even need. After we chose that leg as the pivot point for the torques, we were able to solve for the distance to the cat without even needing to know the normal force. So there you go. Now you go try one.